Right. Greetings, 121 students. I have a chance now to give you some further conversation about electron configurations of ions. The chart from your textbook shows that there are a bunch of ions from main group elements that have noble gas electron configurations. They gain and lose electrons to end up with something that's very stable, tends not to react further. And the examples are interesting because if lithium, beryllium are going to have the same electron configuration as something else that's described as isoelectronic, they will have lost a couple of electrons to end up the same as helium. Interestingly, hydride ion, which is a very odd one we don't run into quite so much, is going to gain an electron, ends up the same as helium as well. The next group that are going to have something in common are the ones that are from the next period, which is the third period, so sodium, magnesium, and aluminum. Each will lose outer shell electrons to end up down at the configuration of only 10 electrons like neon. And conversely, the oxide and fluoride ions of elements 8 and 9 will gain electrons to add up to 10 to be the same as neon. So nonmetals gain electrons. Similarly, in the next row down, the potassium and calcium and gallium ions are formed by losing outer shell electrons, going down from the 19 and 20 of calcium down to the 18 electrons of argon. And the anions that are from the nonmetals are sulfur and chlorine, which have from elements 16 and 17, they only have to add 1 or 2 electrons to end up with the same configuration as argon. So you'll see that there's a lot of things that are isoelectronic with a stable noble gas electron configuration. Note that gallium will make this electron configuration by losing the outer shell electrons, but this is the fourth shell. And so the outer shell electrons for gallium are 4s electrons plus 1p electron, 1 4p electron. Rubidium and strontium and indium work the same way, but they're going to end up at the same by losing electrons down to the element 36, which is krypton, and the nonmetals correspondingly will increase their number of electrons, adding a couple in the case of selenium or 1 in the case of bromide to get up to 36. So they gain and lose electrons to end up with a stable noble gas configuration. You can see the pattern follows the same way with the last group. These asterisks or stars, whatever, are noting here that there are ions that don't have true noble gas configurations because they have also in them an additional field D subshell, but in some ways they're very much the same as the noble gas. So when we look at the electrons of transition elements, or the ions of transition elements, it's interesting to see how those ions are formed. In the case of iron, it has 4s2,4d6 as its ground state configuration, and if it's going to become a +2 ion, then it will have to lose 2 electrons, but the ones that are lost are the ones from the outer shell, which is the 4s2. Same thing as if it's going to make a +3 ion, has to lose 3 electrons. It will begin with losing 4s2 electrons, 2 of them, plus 1 from the 3d6 set to come down to 3d5. So this explains how iron can have 2 different charges. Have 2 different charges. One is the +2 iron ion, and the other one is iron 3, losing electrons from the 4s subshell in both cases, and then 1 from the 3d subshell for the iron 3. So transition metals are going to make cations in such a way that electrons are going to be removed first from an s orbital, the s orbital that's in their outer shell, and that will be the first ones they lose, but then they will also lose subsequent electrons from d orbitals that have a lower shell number. So the 4s electrons are followed by 3d orbitals. And the d orbitals are more stable, so the s electrons are lost first. So take that back to our iron examples. So if iron's ground state configuration is 4s2 3d6, it's at least its valence shell, then to lose 2 electrons we end up with 4s0, losing those 2, or we can just describe it as argon with 3d6. And then iron 3 plus is going to lose the both S and some 1D electrons, 1D electron to end up with 3D5 after the argon configuration. Another example is its neighbor in the transition elements, which is manganese, element number 25, and that is going to have as its ground state configuration 4s2, 3d5. So if it's going to make ions, what is likely to happen? Well, now you can imagine where those 4s electrons, those two 4s electrons can be lost to end up with a +2 charged ion, and the corresponding configuration is argon plus 3d5 for the ion. Guess what? It's the same as what iron 3 has. So there's some things that end up the same, but if they're in different ways, depending upon which element and how many electrons it has to begin with. Okay, so let's look at a couple more things with these. So how many protons, electrons are in these ions, and what's the ground state configurations for the ions? So selenium, pull out your periodic table, is element number 34, so it's going to have 34 what? Well, 34 protons to begin with, and then if it's going to be an ion, it would be called selenide. And so how many electrons? Well, that 2 minus tells you there's extra electrons, so that means it has 36 electrons, and its ground state electron configuration will be exactly like that of its nearest neighbor, noble gas, which is the element number 36, or krypton. If we wanted to write the whole thing out, bear with me. So we'll look at the valence shell in this case. It's the fourth row, so it's going to have, for selenium, the outer shell configuration is 4, for the ion, is 4s2 and 4p6. Yes, there's d electrons in there, but they're not the outer shell. But the selenide ion is exactly isoelectronic with krypton. All right, let's do one with a different number. Nitrogen -3. Well, that would be the nitride ion. And nitrogen is element number, keep looking at the periodic table, number 7. So it would be 7 protons. And if it's got a -3 charge, that means it has extra electrons, apparently 10 total, 3 extra electrons. 10 electrons, and so that means it's going to have the exact same configuration as neon, isoelectronic with neon. In other words, that means the outer shell electrons are going to be which row? Well, it's row number 2, period 2, 2s2, wait a minute, it's supposed to be a 2, oops, sorry, 2, oh, s2, there we go, and 2p6. Now, beryllium. Beryllium is element number 4, so it should have 4 protons. Surprise, surprise. And then if it has a +2 charge, well, that means there's more protons than electrons. Evidently, that means then 2 electrons. And that would give it exactly only 2 electrons in a 1s orbital. Well, what's 1s2, the electron configuration for? It's the same thing as element number 2, namely helium. Okay, let's do one that's got a lot more to talk about. Let's do rubidium. Rubidium, where is that? Group 1 element. It is element number 37. And so that means it would have 37 protons. And how many corresponding electrons? Well, if it's got a plus charge, that means there's fewer electrons. And so in this case, it will be 1 fewer, or 36 electrons. And 36 electrons then, to save ourselves some writing, is exactly the same as what we had on the first example with selenide ion. The ion for rubidium, the rubidium ion, is exactly got the same electron configuration as selenide. Not too bad if you think about what they're doing. You'll always gain and lose electrons when you're making ions to end up with the nearest noble gas stable configuration. So you can refer to your friend the periodic table as needed to figure out which ones they're going to have to gain or lose electrons to become like. Don't forget that the metals will lose electrons and non-metals will do the opposite. They will gain electrons. In a general sense, whichever it is that takes the smallest change to form ions. All right, enough of the discussion of electron configurations of ions for now.